Chemical warfare, how has it changed over the years?
If you go back to back in historic times with Greek fire and they used quicklime and stuff like that, and obviously nowadays, it's much more sophisticated. The First World War and Second World War is really when it kind of kicked off in the large scale. So it went from relatively simple things that they could dig up and easily make that were irritants or flammables to what is very sophisticated, mass-produced irritants in the First World War with things like chlorine gas and sulfur mustard, which is another irritant. To then what we now know, which is commonly the nerve agents that were used in Salisbury, for example, which were first made just before World War II by the Germans, came from agricultural research. They wanted to make pesticides to alleviate world hunger.
Hello and welcome to the Knowness podcast, the vault of knowledge. My guest today is Gavin Smith. He is a chemist who will be finishing his PhD at Imperial College London this summer and our very own chemistry subject lead. He has worked under the supervision of renowned chemistry fellows Tom Welton and Patricia Hunt to develop ionic fluids, synthesize biodegradable polymers, and decompose chemical nerve agents. My name is Naseem Reski, and welcome to the Vault of Knowledge. Yeah. But why are people still trying to perfect chemical weapons and research into it?
To be fair, I think it has, largely declined. I think these days, most countries, luckily, are more on the path of actually kind of getting rid of it. We'll see if that holds up with the global tensions at the moment. But, I think that, there's obviously advantages, if I were a government, to having access to such arsenals because they're very effective. But I think, as with most weapons of mass destruction, they're probably not worth it because, the kind of untold horrors that you can unleash with it. So, to get back to the question, I think luckily most countries are on the path of getting rid of chemical weapons. Actually, research into chemical weapons was banned for most countries with the Chemical Weapons Act of 1980 something, I don't know exactly when, and all the signatories have basically agreed that they won't research it anymore. Now, what goes on in secret or in countries that aren't signatories of the Chemical Weapons Act, I don't know.
Yeah,
nobody knows probably except the people doing it. So yeah.
What's your favorite chemical weapon?
I have no idea. I mean, so my PhD research is on decomposing nerve agents, which would probably therefore be my favorite, if you can say that, because I think they're definitely very, they're sophisticated in what they do, and I do like that their origin actually came from something that was intended to be good. And in fact, closely related compounds are still used as pesticides. So they, it's kind of the duality of chemistry that it can be very, very good or it can be very, very bad. So, yeah.
How does that work? The chemistry behind it?
The chemistry behind it is basically that it messes with the nervous system of living organisms. Originally designed to be agricultural pests, insects. It kind of inhibits it inhibits the ability of the body to degrade neurotransmitters or specific neurotransmitters, which means you can kind of switch your nervous system on, but you can't switch it off anymore.
This is what they use in the sarin Japan thing.
Yeah, exactly. Yeah. So basically your nervous system just gets an overload, and it leads to heart failure and everything because you can't control your muscles anymore. And when they developed it, they were like, this would be great if that could happen to insects. And then they were like, whoa, this happens to humans as well.
Quick question on that. So if they're used as pesticides, does that mean it gets into our food?
Well, it could. I mean, obviously, they've been used as pesticides for a long time, and most of us are still alive. Yeah. So it obviously doesn't get into the food supply to the extent where it would be dangerous to us. It would probably also degrade before it actually gets to us. But the most common, organophosphorus, which is the compound that is most of these pesticides or nerve agents, the most common organophosphorus poisonings aren't chemical weapon attacks because they're thankfully very, very rare. It's most commonly associated with farmers or in agricultural regions where they have access to multi-ton scale of this stuff and then accidentally poison themselves with it.
Reminds me of like Resident Evil. I don't know if you played it. It's very like chemical warfare is like a very big part of those games. Or biological. What's the difference? Now
you're asking
people
something.
don't know, it's a zombie game, isn't it?
Yeah.
Because no one's doing it.
It's because I was going to say I don't actually know. I've watched a bunch of the films.
Yeah. Those I actually really like those.
Yeah. I don't know how it started, other than it started with the Umbrella Corporation. I don't know what they were cooking up in their lands, but it went wrong.
All right, so if we take it back all the way to the start, breaking it down, how would you break down chemistry for someone like me? What are the different areas?
Well, there's a lot of different areas. The main areas, I think, and I hope Musa would agree, also being a chemist, is organic, inorganic, and physical. Those are like the three main core areas, which can roughly be. So organic is kind of organic is everything that kind of the nature is made up of, those kind of molecules. It's a lot of the carbon based, which pretty much all life, I believe, on Earth is carbon based. Then inorganic is a lot to do with metals, transition metals. They do a lot of the catalysts, which are important the public will know them from cars, where the catalytic converters at the end of your exhaust. But they also play a significant role in actually making chemicals, making commercial chemicals like medicine and things like that. Use a lot of catalysts in the synthetic procedures. And physical chemistry is a lot of kind of the core, the core foundations, I would say, of like, core foundations of chemistry is maybe a bit wrong, but it started off, like,
it's like the physics underpinning all of chemistry.
Yeah, exactly.
So
the physics underpinning it. And also, it started off with people like chucking different elements into fire and seeing how they burn, and like, oh, this one burns that color. Like, why is it? Oh, it's because of the energy that's released happens to correspond with this color of light. And it's those kind of, the physical underpinning of
and it's the theory part of it.
Yeah.
Like how to think about what's going on underneath.
Yeah. If you like maths, it's the part for you. Yeah.
So that's chemistry. But what does a chemist actually do?
Well, it depends what kind of chemist you are.
There's good ones and bad ones.
Yeah. Most chemists, I think probably, if you looked at like in society or in industry, you'll probably likely encounter a chemist that's either synthetic. So that is the organic chemistry side, actually making the molecules, because that's obviously important for developing, new medicines, new compounds for everything, new plastics, hopefully biodegradable plastics at some point. Although that does go into a bit of inorganic, but yeah, so it'll mostly be a synthetic chemist. So they actually are in the lab making molecules, or analytical chemistry, which is another big field. It's not kind of one of the core three disciplines, but it's another big one because it's applied to basically analyzing everything, which actually uses a lot of the physical chemistry in terms of what light's emitted, what light's absorbed, and that can kind of tell us something about what is in different compounds. And that's obviously very important because everything's analyzed, from our water supply to the food we eat, to make sure it doesn't have the pesticides
forensics
in we were talking about.
So
forensics, yeah, exactly. Yeah, I have friends that work in forensics.
Also like space stuff.
Yeah, yeah. Oh yeah, like the detecting molecules on faraway planets.
Exactly, things like that.
Yeah, yeah.
That's a lot, yeah.
Yeah, it's methane, isn't it? They look for on. I think
it's like a bunch of things now.
We spoke about this in the last podcast, but would you agree chemists are the underdogs of science?
They're underrated, I feel. Especially in pop culture. We have Breaking Bad now that sort of brought us up.
Yeah, kind of
it's all physicists and biologists.
Well, because Breaking Bad was big when I started studying chemistry, 10 years ago now, which is a bit shocking. But so yeah, I would agree probably, because there's a lot of there's a lot of space-based films that are astrophysics. I mean, I don't think the space-based films are focused on the astrophysicists behind space, but
but if there's a scientist on TV, it's going to be a physicist.
Probably a physicist.
That's a fair point. Yeah, that's a fair point. there's obviously a lot. Yeah, there's a lot of films usually to do with accidentally creating zombie viruses or something. That's more biology related.
Exactly. So it's like,
so I would agree that in pop culture, maybe chemists are
like Jurassic Park
underrepresented.
or biologists.
Oh yeah, that's fair.
yeah,
That's a fair point. Yeah. So where's that film about the warfare?
And they're
agents?
always the scientists are always the bad guys. Like
Yeah.
Breaking Bad is a drug dealer. Jurassic Park, zombie apocalypse.
We know you love films. Are there any movies or TV shows that you love for the chemistry that they show?
Ooh. Well, there's not actually that many. Actually.
Yeah,
We are the underdogs.
It's Breaking Bad. It shows a bit of
So in
chemistry
terms
there,
of
but-
like, obviously Breaking Bad's kind of good. I mean, the chemistry is not necessarily accurate, but I do think it's a nice representation of somebody who.
There's also a bit more chemical engineering, really, towards the end specifically.
When they scale it up to the big. Although that's another interesting part of chemistry, taking something from making it a milligram scale and going all the way up. But yeah, and in terms of films, I think the one that has to do with chemistry that I thought was really good, and I'll mess it all up now because it's been ages since I've watched it. I think it's called Dark Waters or something. It's about the DuPont in the US, basically pumping a whole bunch of chemicals from their plant into the water supply of the nearby village, and they all develop cancer. And it's all about a lawyer trying to take them to court and have them own up. And it really, it's based on a true story. And I'm not sure you'd have to look up yourself how deep it goes, but it was things like the company was claiming, the levels in the water are safe. And then if you look back to who actually advised the government that when they set the levels that are allowed to be in the water, it was the same company pumping them in. So it's like,
I see.
Yeah, obviously they're safe because you're the guys deciding that they're safe. So, so all of that. So, it is based on a true story. And I think it's an interesting part because chemistry is dangerous. It can be dangerous.
The darker side of chemistry.
Yeah, exactly. Even if what you're doing is not the chemical warfare agent stuff, even if what you're doing is pharmaceuticals or important stuff, it can be dangerous for society. I grew up around Basel in Switzerland, which had a huge chemical accident. Again, I don't know when they basically, a lot of the runoff water from extinguishing a fire in one of their warehouses went straight into the Rhine, and it basically killed all the fish. Well, not only fish, that you could not detect living organisms in the Rhine from all the way down to some places in Germany, like for a long, long way. So I think, films like that are interesting because it kind of highlights, okay, this is actually, we do need to be aware of this. We can't let it be unregulated. So that's probably the film that has to do with chemistry that I think was the most impactful. Even if it's not the chemistry itself, it's more kind of the surrounding legislation and everything.
Yeah. And how did you yourself get into chemistry?
Well, as I said, I grew up in Basel, which has a lot of chemical industry. It's a huge chemical hub. And I was 15, 16. I was finishing my GCSEs. Didn't like school at all at that point. Like I think many teenagers, and I needed a job. Yeah. So where do you go when you need a job and what's offered in the area is chemistry? I didn't only apply for chemical jobs, but thank God they were the ones that took me in the end. It was Syngenta, which ironically produces agricultural chemicals. Yeah. It was actually one of their a company that merged into another company that merged into another company that formed Syngenta finally, was one of the ones that invented one of the early pesticides that then became a chemical warfare agent. So it's kind of full circle now with my PhD. But
were your parents chemical engineers?
My dad was a chemical engineer. Yeah, my
is
dad.
That where you lived in a chemistry heavy area?
Yep, that's it. That's pretty much exactly why.
Backstory.
That's exactly why they moved from the UK to Germany / Switzerland, like the border. The border region. And then when I needed a job, came to the chemical industry. Did that for 3 years. I apprenticed as a lab technician. Loved it. And then decided to go back to school and go to university. So who knows if I'd grown up in an area where a different industry had
parallel universe.
Parallel universe, Gavin. What had happened? Yeah.
And did you end up working in the chemistry field or?
So I ended up. So obviously, then the apprenticeship is kind of a practical in a company. So I worked for Syngenta for 3 years while training. It was kind of a 2 days on, 3 days in the lab and 2 days in school kind of apprenticeship. And then after that, went to uni and have been at uni pretty much ever since. So I'm just finishing up my PhD now. And by the looks of it now, I will be working for the civil service come next year. So I will be leaving industry behind me, and I'll be leaving industry behind me. But it just goes to show the kind of, the breadth of jobs you can have with it as a chemist. Yeah.
And obviously I'm with two chemists, so I ask both of you this question. But what's one thing everyone should know about chemistry? If you want to start.
Me first.
Yeah.
Oh, okay.
On the spot.
I wish I'd known this question ahead of time. One thing I want everyone to know about chemistry. I don't know, actually. I guess how versatile it is. We kind of already spoken about it. I feel like chemists have a good idea of, we know a lot of physics from the quantum mechanics level to a lot of thermodynamics. We know a lot of biology. We know a lot of chemistry specific stuff that many other fields know about. And sort of we kind of do all this heavy lifting for the sciences. So it's like that's, and we're really underrated, which is what I said last time. Chemistry is best science. That's what I want to do.
I mean, building on that, I think, and we were saying that we know all this stuff. I feel like I've forgotten all this stuff.
No, but, we knew all this stuff.
Yeah, we knew at one point all this stuff, but as you become more and more specialized, you forget everything.
Yeah,
you don't use, but it is. I think the breadth is very important because it offers a very inclusive environment. Like if you're good at maths, you can still study chemistry and use a lot of maths in chemistry. If you're good at biology, you can study chemistry and use a lot of biology in chemistry. And obviously, if you're good at chemistry, you can also study chemistry. So I think that's very good. And actually, it also serves as kind of, it's very inclusive, but it also means that because you're covering such a wide level of subjects, and I think that's important to know if you want to get into chemistry, there'll always be one you're probably not as good at. And it's like, oh, don't worry about it, because chemistry is made up of 5-6 different kind of areas, and if you're not good at one, you'll be good at another.
Another one,
so,
because how broad it is.
Yeah. So when I started chemistry, I was terrible at maths. So the first year maths course almost kicked me out of the degree. So,
is it?
Yeah. But at the end of the day, down the line, if you don't want to use the maths, you don't have to, because there's so many different areas of chemistry. So it's
Yeah, fair enough.
One more thing I'd say, even though it's usually called a natural science, I feel like chemistry is the only natural science that's a bit more of an engineering-like subject.
Oh, yeah.
Because you're always designing, making things. A lot like, I would say a lot of our synthetic chemistry is basically like engineering.
Yeah. I can see that. I think it does have a lot of room for, well, as all research, but it has a lot of room for creativity. And I don't really know, but I would argue that the people who usually get very far in the research are not necessarily the ones that know the most or whatever, but they're the creative ones that are able to kind of apply their knowledge and be like, well, this works in this area of chemistry. Can we use it for another, or can we kind of? So it's it's that as you said, which I think is again, a lot of engineering is that as well, because at the end of the day, it's application based, which not all sciences are necessarily.
Follow-up question on what you just said. You said you're not a big fan of maths. So how did you end up doing a PhD in computational chemistry then?
Yes. It's actually, I mean, I suppose it's down to me liking to challenge myself. I get frustrated when I think that I undersold myself somewhere. So when I left school and did my apprenticeship, I loved the apprenticeship, but I very quickly realized that everybody that was my boss or my boss's boss had a degree at least, or a PhD more likely. So I was like, well, I'm not going to get very far with my apprenticeship. And that being said, it's an amazing system. So you can happily work at that level and earn a decent salary and climb kind of salary brackets and all of that. So that's perfectly fine. But I was like, actually, I kind of want to challenge myself school wise. So then I took myself back to school, and the same was true in when I started the chemistry degree. I was like, maths is really hard. I hate it. is terrible. And then by the end of my bachelor's and my master's, I was like, oh, looking back, this maths wasn't hard. I was just kind of overwhelmed with starting uni and doing everything else and kind of, fitting in and trying to be a human being while being a chemist, So I was like, oh, actually, I feel like I could do better at this maths. So then one of the areas I'd completely disregarded was computational chemistry, because it's maths based, and actually the professor that was teaching us the maths in first year was a computational chemist, which is quite common that they kind of take those entry-level maths courses. So I'd kind of chucked the baby out with the bathwater when I said, oh, I don't like maths, all of this goes out. And then later I was like, oh no, I think this is, I should have paid more attention here. I should have, I feel like I feel like I could do more of this. And then it coincided with the pandemic, where something like computational is very valuable because you can do it from home, which is great, which you can't with most lab-based subjects. So I was then looking into that. The first time I actually kind of came across computational chemistry and thought this would be interesting was I did an exchange program with the US, and the professor leading that exchange program was a computational chemist by trade. Although he would still refer to himself as physical organic chemistry. So kind of the interface between physical and the organic world. And I, coming from the organic world, was like, oh, this is really interesting. Here's somebody who is quite clearly a computational chemist, but still refers to himself as physical organic. And me as an organic person can actually understand what he's talking about. So that's kind of, maybe I should look into computational chemistry. Then the pandemic happened and I thought, I should definitely look into computational chemistry because it lends itself to the situation we're in. And then I started reaching out, and luckily the professor, Tom Welton at Imperial that I'm doing my PhD with now, has a very strong collaboration with Professor Trisha Hunt, who's in New Zealand. And when I reached out there and said, I'm interested in, at that point it was final year master's projects and then also PhDs. He said, I have a PhD coming up that you could, if you're interested in, you can apply for that. And also the collaborator in New Zealand has a project we could do for your master's project. It would be predominantly computationally based. And I was like, oh, this is really good. I can learn this now and hopefully apply it to my PhD. So I kind of went from, thinking I hated maths to realizing now I just, I panicked. And then coming back to it later in my academic career.
I remember you told me a very different story for when I asked you how you got into computational chemistry. But less profound story. It was how you were tired of working long hours in the lab.
So that's a fair reason.
And you saw these computational chemists just drinking coffee on their desks, just chatting with each other. And that's where you were like, I got to get into that.
Yeah, well, you've kind of outed me there, because that's a bit unfortunate. Obviously, computational chemists work very hard as well. Of course. But there was one aspect that okay, if you can say obviously the working hours and everything, but also just the flexibility. They can work from wherever, how it suits them. But it was in the US where in the US they work a lot. Especially in academia, 6-day work weeks are commonplace and everything. And everybody in the synthetic labs was staying till like 6, 7 till after dinner. And I looked across the floor and was like, it's interesting. There's a bunch of empty desks there. They've all gone home. And it's 4 o'clock. What happened there? And then it's like, there's the computational chemist. And I'm like, interesting. Sign me up for that. So that is definitely also a reason.
That's interesting, because I think you told me about the work culture in America being different in the UK, because I think you told me that you had a friend who went to Japan and the work culture there was very different. So could you give us a bit more of an insight into academia, especially science, and what the work culture is usually like?
I think the main thing with academia is that people have to realize if they're interested in getting into academia, obviously at the kind of level of a student level, not working as a professor in academia, because I have no experience with that. But in terms of a student, the most important thing to know is that you can't compare academia with academia. It's always a microcosm of different research groups, and the culture can differ even within an organization. The culture can can differ hugely between research groups. And a large driving force of that is obviously the professor or PI, primary investigator, principal investigator. I call them professors because that's what you call them in Germany. PI is the British term for it, or the American term. So it very much comes down to that, and that's kind of the key feature. Now, obviously, different countries also do it differently. So the US is very, it's interesting. They start their research from much earlier on in their academic career. There's bachelor students who, beyond like not just doing their final year projects, they do it as kind of extracurricular. Usually, actually, I said you did medicine, but usually it's to bump up their CV.
Yes, this is That's the reason I'm trying to do it.
It's to bump up their pre-med students that want to go to medical school, and it looks very good if they've done lab-based research. And then, so that's what I can kind of talk about, because I've been to the US and I've seen the culture there. I've been to Germany as well, which again tends to be a little bit more rigorous. Not necessarily in terms of working hours, maybe not different, but they definitely like teaching chemistry from the foundations up, and maybe forget kind of all the modern trends like computational chemistry, which really they should put much more of an emphasis on because it's a big thing. And then Japan, I have colleagues that went to Japan. While I was doing a research project at Bristol, actually, the PhD student supervising me there went to Japan for 3 months, and then one of the PhD students in my lab currently did his postdoc in Japan. And I believe it's completely different there again. But it's also, what I've heard is it's also different for Europeans that go there. So they have one standard that they apply for Japanese students, and then I've heard it's kind of the light version for Europeans, because they're like, these poor weak Europeans, they can't work as much as we do.
You told me a funny story about the desks and the way they ordered the desks.
Yes. So again, this is an anecdote, and I hope I'm telling it properly. But basically, it's relatively hierarchical, which is again something you notice that's different from different countries. So growing up in Germany is much more hierarchical than the UK, and Japan is obviously, by the sounds of it, a bit more, because the way they organized their desks was, every year there was a review of who was the best PhD student with the most output in everything, and that person got the desk closest to the professor's office. And then it kind of worked backwards from that until you were like sat next to the bins in the corner somewhere. You were the disgrace of the research group, and I know where I would sit, but we won't elaborate on that. So that was very interesting.
So another interesting difference between countries, especially with the US and the UK, is how long PhDs are.
Yeah.
So I think in the US, they can be like 5-6 years long. And I think their undergrad is like way longer as well. They spend a lot more time at uni.
So in the US, so again, it works slightly differently, the PhD, because it's officially, I think, called graduate school rather than just a PhD. So it's you do your undergrad, which is longer. I think it's 4 years instead of 3, which is commonly, commonly the undergrad 3, right? Here, for the bachelors. I think a large part of that is obviously because they have the major minor system, and it's
more flexible.
Yeah, they spend their first year basically deciding. Again, best ask an American to confirm this, but they spend their first year deciding kind of what they want to study. So it's much more flexible. And then after your 4-year undergrad, you can go to graduate school, which here would be like the MRes programs, which are postgraduate research programs. Technically also postgraduate masters, so all of them that aren't integrated would also technically be graduate school, and then also PhDs. And graduate school is, I believe the standard is 5 years, and the first 2 years of that is basically a master's degree. So if you decide to do graduate school and for whatever reason you leave after 2 years, you get a Master of Philosophy rather than a Doctorate of Philosophy, which is the PhD. So yeah, it is longer, but it's basically longer because they do rather than integrating their masters into their undergrad, which is common over here, you integrate the masters into your PhD.
Okay, that makes sense.
Which is similar to what they have in the UK is called Centres for Doctoral Training, CDTs. and that's another way to do your PhD. So mine was, I applied straight to a professor who had funding, and that was a 3-year program. It can also be a 4-year program or 3.5, but mine was a 3-year program. And but there's also centers for doctoral training, which will take a bunch of people and then distribute them between groups in the university. So it's more like you're applying to a university, or sometimes it's a cluster of universities that have one of these centers. And they are run as 4-year programs where the first year is a master's. So again, if you do the CDT and you leave after your first year, you get a master's and not a PhD. So that's kind of, as Britain loves to do, they follow the American trends.
Well, which system do you think is the best?
It all has pros and cons.
Yeah.
As I said, when I was in the US, I really did like the fact that they're exposed to research very early on. Now, you could argue it was compulsion because they needed it for they needed it to boost their CV to go to med school because it's very hard to get into. But I did like the fact that, I went there at like late master's level when I was at the end of my, which again was a longer course than it is in the UK because Germany has longer degrees. And I was very impressed with how like active the bachelor students were in the lab as an extracurricular. They didn't have to be there. They just decided to be there. And I really liked the fact that they were exposed to research early on. Now, I feel like it shouldn't necessarily be an extracurricular. It would be nice if it was actually integrated into the course. But that was very good, what I take from there.
Yeah, well, I was going to say something you said earlier. You said your PhD 3 years?
Yeah.
Well, we read online that you started your PhD in 2021.
Yeah.
And as far as we know, you don't have a PhD. So what's going on?
Wow, thanks, Musa. So it's all gone wrong. But no, that's also relatively common with PhDs because the kind of core time is usually spent on the actual research, which doesn't necessarily encompass the write-up. Now, if you're very organized and very driven, because that's the other thing as well, that PhDs are almost open-ended in the sense that there's so much you can research, even, on a relatively small topic. Because, I'm looking at chemical warfare agents. I'm looking at how to get rid of them, nothing else. I'm not looking at how to make them. So I'm looking at how to get rid of them. Sure. I'm only looking at a specific subset of chemical warfare agents and nerve agents. And then technically, I'm only looking at a specific subset of the nerve agents. But with even going so deep, there's so much that you could do that it really does, technically it's open-ended. It's just at some point you yourself personally have to be like, no, I think I have enough now and I want to write up and finish. Now, it depends kind of on group culture. Some groups are very adamant that it's like, no, okay, whenever your funding stops, you'll finish 3 months beforehand and write up. Other groups are more like it's, you'll get as much as you can in the time you're paid for. And then, I know some people move home to their parents or whatever and then write up at home. In my case, I wanted to stay in London. So I kind of managed to get my professor had 3 months extension of the funding. So got 3 months up until that was just before Christmas, basically. And then another supervisor had another chunk of funding that it was available for after Christmas. So I kind of found my own jobs and funding. But yeah, the time I was researching my topic was the 3 years I was funded for from July 2021, that was, up until officially July 2024. But then 3 months extra from my professor. So it took it to late 2024. And now I have a job as a postdoctoral research assistant, essentially, that I'm writing up while I'm doing that job. So another job in academia, it's just another research position in academia. And I help out with kind of some of the administrative tasks in the lab. But yeah, that's kind of why it takes longer, because either you need to be very organized and also, very confident in your own work and know I have enough now and I can write up. And then you can do it within the 3 years. Or like me, you take longer and then you need to find other jobs to kind of finance yourself. And at that point, you're trying to write a thesis while doing a job. and now also doing this for Knowness. So it's like, oh, at some point I'll get my thesis written. Right? So luckily,
we'll get that some point.
Yeah, luckily it is now actually coming to an end. I have it pretty much all written, and
Okay, that's really good.
yeah. And I have I have my examiners for the Viva chosen and everything, and we will have it submitted by the end of July at the latest. So we're getting there.
Yeah.
But yeah,
Dr. Gavin Smith soon.
hopefully.
Next time you're on the podcast.
Like, let's not jinx it now, everybody. Yeah.
What's your thesis on? Is it like how to make chemical weapons for dummies, or?
No. It's literally it's titled. I know this because I recently had to put it into the form when I was trying to choose my examiners and everything. It's Ionic liquids as reaction solvents, the decomposition of chemical weapons. So so that's what it's titled, and that's kind of what it's on. It's on decomposing chemical warfare agents, specifically these nerve agents that I talked about, with a class of compounds called ionic liquids. So that's what it's on.
Do you want to tell us a little about these ionic liquids?
Yeah, so I mean, ionic liquids are generally, well, they're salts that are liquid. So if people have done, I don't exactly know when it's taught in the UK, but if people have done like GCSE level chemistry, you'll probably have been taught at some point that salts are commonly crystalline solids, like we know from table salt and other household salts essentially, but commonly it's table salt, and they're usually associated with, well, crystallinity, they're brittle, and they have very, very high melting points.
Remember the melting point for sodium chloride?
I have no idea.
He's supposed to know.
You should know this. It's 801 degrees.
Yeah, you see. So
so 800 degrees Celsius. That's crazy.
So that's that's beyond what most people work at. Even in industry, for example, working at that temperatures, you're looking at like furnaces and like metalworking that gets to those temperatures. So generally, people don't use salts in liquid form. I think one of the big processes that does use those high melting salts in liquid form is making aluminium, because they melt the salt with various techniques. But then ionic liquids are salts that aren't crystalline solids, but commonly they're liquid at room temperature.
Gotcha,
which again is kind of, this is science. They'll teach you something like, oh, salts are crystalline solids with high melting points, boom, and then you'll learn that. And then years down the line, it'll be like, it was all a lie. Not all salts are crystalline solids with high melting points. Yeah. Here's a subset of them that actually melt at low temperatures, and they have all kinds of weird and wonderful properties that are being explored for various different applications.
I think it'll be really useful for you to explain like where does the high melting point of typical traditional salts comes from, and then why ionic liquids not melt at much lower temperatures, because that really gives you maybe an audience an insight of how a chemist thinks, where the rationale of things like that comes from.
So if we take sodium chloride for an example, it's basically because it has something called an ionic bond, which means the electrons that make up. So what makes up an atom is basically protons, positively charged neutrons, and they're in the core of the atom, and then you have electrons around the outside. And when they come together to bond, they basically share electrons. Now, ionic bonds are an extreme form of that, where they share them to the degree where the one atom gives up electrons to another atom. So in sodium chloride, it's the sodium that gives up electrons to the chloride. So you actually have a positively charged sodium and a negatively charged chloride, and they stick together very well. And they're relatively small, so they can pack very nicely in a crystalline structure where they're all kind of positive, negative, and that repeated in the crystalline structure.
And they're also just single atoms, so they're perfectly symmetrical.
Yeah, exactly. Yeah. So the crystalline packing, it's called, how it's actually packed up in these crystal structures is very easy and very organized, because that's basically what solids are. Is they are highly organized in their crystalline lattice structure. There's exceptions. Glass, for example, which is called amorphous solids. They're not organized. It's kind of a rare one where it's a solid, but it's not actually organized crystalline lattice. But generally,
They almost look like a liquid if you like just see them, like a picture of them. Like
Glass.
zoomed in. Yeah, it almost looks like a
well,
liquid. It's all messy.
There's
You would think it's like flowing, but then you look at it, it's actually solid.
so at some point, and I think this is kind of fake news, but when I was back in my apprenticeship, I was told that if you look at really old windows in churches and everything, they're usually thicker at the bottom than they are at the top. And somebody was like, "Oh, that's because
The glass flowing down."
that's because it's glass flowing down." But in reality, it's just how they
Made.
It's just how it was made back then, that they couldn't, they didn't get the uniform thickness properly. But even though it's fake news, I do think it kind of, it does, it shows very well how you can imagine glass, because you can imagine it from the structure as a really, really, really viscous liquid. Now it is actually a solid, but
It's frozen.
Place. It's a frozen liquid, basically. So it all comes down to the packing, basically. Does it like to be a very organized, rigid structure?
Which causes the high melting point, because it's
causes,
really hard to pull them apart.
Because you have, because I mean, we know from things that are positively and negatively charged, they like to stick together. And now, if you then have a crystalline lattice of that, where you have,
Thousands of positives and negative
charges
they can
next to
literally
each other.
get really close to each other because of the spherical shape.
Exactly. Yeah. That's why it has a high melting point.
Gotcha.
So how do you make a low melting point?
So generally, it's exactly that. You need something that doesn't like to, or isn't able to pack very closely to each other. Because in nature, it's a force called entropy. It's basically, you can imagine it as the chaos force that likes to have things chaotic and non-organized, and that if you're forcing something to organize, like in a crystalline lattice, you're having to overcome this entropic force that wants it to be disorganized. So for something to be in a lattice, it needs to be able to form strong energetic bonds like the ionic bonds. So if you don't allow it to pack nicely and don't allow it to form these nice lattices where it can have this energy to counteract the entropic force, then it won't. Then it will prefer to be a liquid or even a gas. Salts aren't really gases. That's one thing that hasn't come about yet. But yeah, that's kind of it. So you need to make an anion and a cation, which is the positively and the negatively charged bit. So the anion's the negatively charged and the cation's the positively charged bit. You need to make them that they don't like. They're usually, big, much larger molecules. So not just a spherical atom. They're molecules made up of a bunch of different atoms that have a lot of freedom, so they can kind of wiggle about a bit and all of that. So then when you try and force them to stick together in a crystalline lattice, they don't actually like doing it. And because they don't like doing it, they don't gain as much energy from sticking together. So at the end of the day, they prefer to be in a free state where they flow like liquids.
And that's why there's a lower melting point.
Yeah, and that's why the melting point is lower.
Cation, they're usually asymmetrical as well.
Yeah.
So they're literally designed in a way where there's no good way where you can put them together and make a lattice out of them. So there's a lot of geometry. It's just simple geometry in a way.
Okay. And do you both share sector research? Is that right?
We were in the same research group.
Oh, is it?
For a while.
I was going to say,
for a brief period in time, we were in New Zealand. Actually, took us all the way to New Zealand to meet. But
is it? That's how you guys met.
We were both doing research in computational chemistry. Actually,
you both know quite a lot on this topic. So
I think. You didn't go into the topic because of the ionic liquids, did you?
No, I didn't know what an ionic liquid was when I landed on New Zealand.
Because I was going to say, we forgot to completely mention as well, you guys know each other.
I just saw the lab research group, and it was the most hardcore theoretical and physical chemistry and quantum mechanics like I could find. And I was like, that's what I really want to do. It's like, I'm going to go do this. I had no idea what an ionic liquid was. And the rest is history.
But now you love them, and you couldn't live without them. That's how ionic liquids
are
impact.
cool.
They're quite nice.
But it's okay with ionic liquids. What are some uses of them? Because the whole process behind it is kind of cool. But
Yeah, so
There's a lot of uses. But
there's a lot of uses. Yeah, it was kind of if you go back, so they've not actually been around that long. And really, the hardcore research, or when it really peaked in terms of, oh wow, these could be really useful, is only actually turn of the millennia. So before, they were known beforehand, but it was quite unique to be doing research on them. And then came the period of time, I would say, where people claimed you could do everything with them. Like any application that used a normal liquid, people were like, and we can do it with ionic liquids.
It's like that now with AI.
Yes, exactly.
And we can do it with ionic liquids, and it will be great.
It's a honeymoon period.
And then now slowly it's kind of crystallizing out what they can actually do. The big thing
nice
now.
Pun.
Sorry?
Good pun.
Yeah.
Oh yeah.
Didn't realize.
So the one of the big things that they do is biomass processing in terms of cellulose and stuff like that. They're trying to make, or they can make like almost plasticky films out of cellulose, like cellophane, just with an ionic liquids process. That's kind of a relatively big one that ionic liquids are used for. What I'm looking at is a very small subset of it. There's not many people looking. Well, there's not many people at all looking at ionic liquids for decomposing like chemical warfare agents. Although I do think it has a lot of potential because ionic liquids are still salts. They have a very high boiling point, so they won't evaporate. They're non-flammable. So there's a lot of things. If you want to contain something that is very, very toxic, you kind of want to do it in a liquid, or that won't itself evaporate away, or cause some issues I
think it'd be really useful if we take a step back and actually explain from the structure that you've already explained what are the properties of ionic liquids, and then move on to applications. So what are the properties? So things about like the low volatility, and how do you relate that to the structure? Because I think that really help an audience to understand really how a chemist thinks.
So basically you still have, going back to why things are crystalline and or not, you still have these very high ionic energies of the positive and the negative charge needing to be close by. So
what that means, even though it's a liquid, it's still really strongly attracted to each other.
Yes. It has a lot of energy in it, essentially. So if you try and break those bonds completely, like if you evaporate it, which is ultimately what you're then doing, is you're taking all the molecules and all their interactions and saying, well, we'll get rid of, in an ideal gas scenario, which is something commonly referred to in chemistry, the ideal gas scenario is you have one molecule that is interacting with nothing else because you've evaporated it and the volume around it is so large that it's not interacting with anything else. So that's kind of the concept of evaporating something, because you take a molecule that's interacting with a whole bunch of different molecules and you put enough energy into it that it comes out of that and interacts with technically, nothing. Obviously in practical terms it's not, because even in the gas phase it will interact with other gases and everything.
And everything's interacted with anything.
Yes.
Yeah, everything. Schrödinger's equations.
Exactly. But that's kind of the idea. Now, if you try and do that to something that has so much energy, and even in terms of the ionic nature, it's very, very hard to kind of evaporate out. Now, you can, under very high temperatures and very, very low pressure. So if you take the external pressure right down to like a really, really low vacuum, you can actually get ionic liquids to go into the gas phase. But even then, they will go into the gas phase as the anion cation together. So you've still not technically separated them out so far that that they don't interact with, because they're still interacting with each other. So there's that energy between the plus and the minus is still there even in the gas phase. To truly split them would take a lot of energy. So that's kind of where it comes from, that they're non-volatile, which means they don't like to evaporate. So if you just have them, even if you just have them lying around, you'll know some volatile chemicals like, something like petrol, for example.
Yeah.
Ethanol,
like any organic.
one of the things is you'll smell it a lot because it means that a lot of it is coming into the gas phase, which can then reach your nose and you smell it.
Yeah.
Water, for example, is actually another one that isn't very volatile because it has a lot of energy in the water as well.
Yeah, because it's a polar solvent.
But even that, if you just leave it out, like if you've had a shower in the evening and you go into the bathroom in the morning, the water on the floor will be gone. But ionic liquids don't have that. They
just stay as they are.
They'll stay as the liquid they are.
And just to help you picture it, they're not even that liquid.
No.
No.
That's the other thing with that. There'll be a lot of people that claim, I work with ionic liquids, and a lot of them are kind I solid.
They're like honey-like.
Yeah. So even the liquid.
When I imagine it's kind of like lava or kind of like honey.
Yeah.
That's a good way to imagine it. Actually, a lot of it So there are relatively runny ones. Mm-hmm. If you compare it to water or something like that, they'll still be really viscous and everything. But you can go all the way up to them being about as viscous as honey, and you can get them to It's like something like Marmite is like, oh, is it solid? Is it a liquid?
So they're in this weird in between zone where the intermolecular interactions are strong enough.
To
keep them viscous.
But again, you also kind of have to imagine if you're looking at normal salts that melting points of hundreds and hundreds and hundreds of degrees, then obviously, even if something comes down and has a melting point of 50, where, it's not technically a liquid at room temperature, compared to what a salt is, it's still really easy to liquefy. So that's kind of one of the characteristics from the nature of it being an ionic liquid, that it has a very low volatility. For the same reason, it doesn't really burn because if you look at what burns, if it's not the liquid itself that burns, it's actually the vapor coming off the liquid that burns. If you have like a petrol fire or something, it's not the liquid that's burning, it's the vapor above it. Even if you burn a candle, for example, it's not actually it's the wax burning, but it's the wax that's melted and been drawn up the wick, and then it's actually the wax that's in the gas phase that's burning.
Because the petrol easily vaporizes, so it mixes with oxygen in the air very quickly.
And then ignites.
So it's very good for combustion.
Exactly, exactly.
And this is kind of what your PhD is basically about using this to dispose of waste. And have you seen Sopranos?
No, I haven't actually.
I was going to make a Sopranos joke. He's like a waste management consultant, but but after this PhD, what are your plans?
After the PhD, so as I said, I am not actually going to stay in research. I'm going to the civil service, working for the government office for science, which I'm very excited about.
That'll be really cool.
Yeah, going to start in October, I think.
Okay.
And so a bit more kind of policy related, using science to kind of advise policy and things like that.
Yeah, so when you get that role, hopefully, technically we'll have a government official on Knowness.
Hopefully.
Can you tell us a bit more about your role in Knowness?
My role at Knowness is basically a subject lead for chemistry. So I've always been very interested in chemical education, partly because I've experienced it in so many different countries and this is interesting how different places do it. And what I do here is kind of assist with the course design for chemistry. And I write the courses Musa did a good job at that because he was the subject lead for chemistry before I started. So big thanks to Musa for freeing up my job so I can come in at Knowness.
I'll just wait for the next course.
What happened? Did you get fired or?
My what?
Did you get fired? What happened?
I got fired.
I think it's more accurately he was promoted out.
And promoted to Chief Learning Officer.
Exactly, Gavin can fill this lowly role that I left behind. And I gladly did. It's been great.
You did tell me that you really wanted to go into education. So I thought this was perfect.
So exactly that. So I really enjoyed it. And it's kind of nice, to actually write the courses on it and everything. So that's kind of what I do here.
So I want to show you a picture now. What advice would you give someone like this person who wants to get into chemistry? If I want to have a little look.
Oh, nice. Taken from my. Well, he's an ideal person to get into chemistry.
Very ideal person. Yeah.
I even had hair back then. Although it was already thinning. So, that's before the degree.
Is that World of Warcraft or is that?
I think so.
That is Warhammer, I think.
Oh, sorry.
I thought it was the same thing.
No, World of Warcraft sounds
Got it.
So that's at the Gamescom. Oh, let me think how old I must have been there.
Oh, it's Gamescom.
Yeah, it's Gamescom.
Oh, I was on to go. That's so cool.
In Germany, yeah. So it could have been when I was 18 because I went for my 18th birthday because I'm a cool guy.
Yeah. That's sick. I wish I had it. It's a big gun as well.
Yeah, I know. Thanks very much.
You look very serious in the pace, very solemn. Very not phased at all by the massive ogre behind you.
It's an orc, but it's okay.
Get it wrong, man. It's an orc, all right?
Well, if you know the Warhammer universe, it's a very solemn universe. So you can't be.
That can't be business mistakes, man. Fake chemist.
Fair.
So that guy.
What would you tell that guy?
I recommend just do it. It's it's
and in general, like people that want to get into it, have an interest in chemistry. Any of the viewers, maybe?
Yeah. I mean, there's so many different ways into it. I mean, obviously, I started with an apprenticeship, which I think chemistry also does lend itself to because at its core, it's an applied science. So it is applied, as I said, in the analytical world everywhere. So you do need kind of entry-level, apprentice-level kind of positions that do that kind of chemistry. So you can get into chemistry like that. And the apprenticeship scheme here in the UK actually, I think, allows you to kind of climb up through and then do degree apprenticeships at some point, which in Germany you can't. Basically, once you've done an apprenticeship, you have to go out of that world to then do academia. Whereas here, I think it's much more mixed. So you could even start doing it like that. If you want to get in a more traditional way through university and everything, I would just recommend go to open days, kind of listen to podcasts like this, figure out does it sound nice?
Or the chemistry taster course that Knowness.
Yeah, exactly. Yeah,
Post 16 and pre 16. There's two versions of it.
Yeah, exactly.
It's got video content.
I'm actually still working on the other version. Wait a moment.
When it's ready.
Watch Breaking Bad a couple of times, and then you're all set.
Yeah, Dark Water as well.
So. Duck water's a little bit negative about the chemicals.
Let's not get into that.
If you go into chemistry looking at that, you're probably going into chemistry to be an even villain or something.
It's like watching Chernobyl.
That's a spoiler to be fair, but
it's like watching Chernobyl before getting into like nuclear chemistry.
Nuclear physics,
Nuclear physics, sorry,
So I would just recommend, you kind of look into it. Yeah, looking into it. And diving into it is a good word because it's such a broad topic. If you like science, any science really, you will find a home in chemistry. Yeah, it's essentially it because
the foundation of science, like you guys
mentioned. And you can move on to a different science afterwards, like I am. Yeah, because it's very easy transition.
Yeah. So if you're torn, obviously I'm biased, but if you're torn between maths and chemistry, do chemistry because you can always decide. Okay, you'll do a lot of general chemistry at the start, but if you really want to pursue it, you can pursue maths within chemistry.
Oh, that's true.
Whereas I think it would be much harder to do maths and then suddenly, I want to be a chemist.
We won't tell it to our maths guy.
Listen. Yeah. The maths we do in chemistry, math people will be like, what the hell are they doing there?
Yeah, I don't get into that.
But for real world applications, you can really do chemistry and do a lot of maths in chemistry. Yeah.
And for someone that wants to get into a PhD, what advice would you give them? Because I know you're thinking of, you're actively...
3 offers.
Oh, okay.
Oh, look at you go. I got one, thank you very much.
So what's some advice you'd give to our friend over here?
Oh, sorry, no, I got 2. Thanks.
Two.
Not as good as Musa, but that's okay. Again, if you... So I think a PhD is different from the other degrees. So you should go into a PhD if you've enjoyed the research aspect of chemistry, because it's much more about your own kind of research drive and how inquisitive you are and do you like the best PhD students and researchers I've always found, and it's something I'm not that I struggle with, but I'm always impressed with people that really kind of live that. Is you see people who something goes wrong in the lab, and I get frustrated, and there's other people that are like, wow, what went wrong there? Like, why did the reaction not do?
More inquisitive.
Why did the reaction not do what we thought it would do? And then they spend months trying to figure that out, and then they do. That is essentially research for you.
Gotcha.
So it's this really kind of deep dive of trying to problem solve, figure out what's going on. If you enjoy those aspects of chemistry, then I think a PhD is really for you, and you should 100% go for it, because it improves your career chances outside of academia, and obviously it opens up a lot of career chances within academia that you just don't have if you don't have a PhD. That's kind of who I would recommend it for. Also, if you're thinking of continuing to work in the chemical industry, as in lab-based roles, things like that, I would also, I would say you should look into a PhD, because you will encounter the fact that there's a lot of PhDs around you then, even later. So it could be limiting if you don't have that degree to how far you can get. You may, whereas if you have a PhD, you could be running the lab, or, be a more senior scientist along the way. If you don't have a PhD, your career could you could start in the lab and, end in the lab, because that's kind of what you do, which is perfectly fine if that's what you want. But if you want to stay in a lab-based career and climb, I think that's kind of the area where a PhD would be good.
I see. Yeah.
If, for example, you want to leave university and do a graduate scheme in consultancy or something else, you don't really need a PhD. You can, by all means, you can do your bachelor's, master's, and have a look for that. But if you really have that hunger for research, then I think a PhD is for you.
Gotcha. And just to end this episode, you have a final segment, the Mythbuster segment.
Okay, yeah, great.
What's one chemistry myth you want to debunk for us?
You did one earlier with the church glass paint myth.
Oh yeah, that's a good one. That's a good one. Yeah. Coming to Breaking Bad.
I was literally going to say,
that's coming to Breaking Bad.
You mentioned earlier there's some inaccuracies.
The hydrofluoric acid they used to dissolve the body in spoilers.
That's early on,
like season 1 or whatever. That's not the acid.
Really?
It's not the acid you use. Like,
what acid would you use?
You
phrase it in such a way like I have 3 options in my head.
So
it's like a tier list. I
have an idea as well, but carry on.
Yeah, so to dissolve organic matter, I'd use sulfuric acid mixed with hydrogen peroxide.
That's exactly what I was thinking. It's exactly what I was thinking.
So if you
hypothetically,
there's something called piranha acid, because it eats up organic matter so quickly. And it's a sulfuric acid based acid, and then so that's what I would use. Or you could use bases, which is the opposite of acids.
Really?
The alkaline substances. Like sodium hydroxide. A lot of drain cleaners are based on alkaline stuff, and it's also because they're good at dissolving organic matter. In fact, the kind of process of I believe it's called biocremation or something. You can, instead of being buried or being cremated, you can be biocremated, where I believe I don't know. I've not looked into it, because I'm hoping not to need that for still quite a while. I believe they dissolve bodies in
bases.
In bases and alkaline substances.
I didn't even know that.
Again, I've heard it leaves behind like a green sludge. So so that's that's what you do.
Shouldn't be called biocremation. It should be called chemical.
Yeah, I know. Again, we're underrepresented
exactly.
in
we're getting biowash.
Chemistry washing is just.
Well, if you look at all the Nobel Prizes recently, the Nobel Prize in chemistry has also kind of often gone to biochemists, which again is like, oh come on.
We should ban but the Nobel Prize for CRISPR, that was a chemistry group, wasn't it? That was a medicine.
To be honest, I don't know who did that, but that would be. I
think it was a chemistry group.
Yes, we're going into other sciences.
We're getting there.
The hydrofluoric acid they used is not actually a particularly strong acid. It has some unique features. It has some unique features in terms that it, for example, can etch glass, which
Okay.
not many acids can.
Yeah.
But it's not actually strong in terms of dissolving things. It will kill you painfully. But
we won't dissolve it.
For dissolving a body. So that's that's
it's a very unexpected way to end the episode. But yeah, thank you guys for joining us once again, and thank you for being an excellent guest.
Yeah, thanks for coming along.
Thanks for having me.
As well.
Great,
Fantastic.
All right.
Until next time.
Thank you very much.